Greetings, everybody. We're back for another edition of Stat 5114. We've played around with varying technological resources. I think we're kind of fixated now on using Zoom for the live sessions, and we'll get the static film stuff uploaded within a few hours of this class. I want to go over today mixture identification and inference. We won't get through all of this. This will probably take us a couple days to get through everything, so we're going to park it on this and learn an algorithm that sometimes we use to solve the mixture identification problem. So we've been solving a lot of problems where we kind of just write down our likelihood model. So likelihood theta given some collection of data is proportional to something that looks like this. And so where our likelihood is induced by just kind of something that we can write down pretty easily. So this might be a normal distribution or a Poisson or something in the exponential family. And we've learned how to kind of think about maximizing parameters in here or doing Bayesian inference by multiplying by a prior. Mom estimators are induced through some function that is not the likelihood, so they don't play around with this function per se, but a lot of people just write down this relatively straightforward likelihood. With mixture models, I'm kind of thinking that you've got different underlying distributions right here. So this might be F1, this one might be F2, and this one might be F3. And they're all going to have their own parameter sets. So this is going to have all the data that was created under this model right here. I'll call that X1. I'll say it's conditional on its parameter set, so I'll call that theta 1. And so on and so forth. This will have its own data in its own parameter sets, and this will have its own data in its own parameter sets. And there's a big part of this problem you never get to see is you never get to see which distributions actually induce these different modes. You don't actually get to see which distribution a particular data point came from. And so you have to infer that as well. And Sierra's going to take you through an algorithm that a lot of people do for this maximization called the expectation maximization algorithm. So expectation maximization. So there's two steps involved. One is you perform an expectation, and then you perform a maximization, and you iterate over these two processes. And if set up correctly, you'll be able to figure out what these underlying parameters are from all of these distributions. So just remember, this is x2 given theta 2. And this is going to be x3 given theta 3. So I'll be more clear about that. That's just a scribble to tell you where we're going. So Sierra, I think, has got 2 lectures planned for us on expectation maximization algorithm. And where that comes from is before the world pandemic, I had a couple plans that I was going to tend to this week. And those have since been canceled, but I thought it was a good idea. We're just going to keep trying to do the class the way that we had intended to do it. So Sierra's got 2 lectures planned for you. I'm going to run the Zoom session for her, and so I'll be in the room as well. And she can teach you everything she knows about this algorithm. This algorithm is presented in the book. It's a little bit terse, so read through that maybe before next time's lecture, and you'll be able to be a step ahead. At least what are the steps in the algorithms, and there's some notation you might get confused about. So if you've already read through everything, it won't surprise you the first time around. Before we delve into this problem, I want to back up and talk about this problem one more time. So xi's are distributed uniformly between negative theta and theta. I goes from 1 to n. Here's the distribution right here. And here's some data points in here. Here's the minimum, this is the minimum, and this is the maximum. So the min and max order statistics. And we kind of know that it's those order statistics that are minimal sufficient, because they're the one budging against the corners. And I said, when we first confronted this, it's really which one is closest. And can you know? So we've had some debate. Is this two-dimensional or one-dimensional, the minimal sufficient statistic? And what is the likelihood function for all of this? And so let's just remember what we wrote down last time. So we ended up writing down that the likelihood function, given all of the data, it's of course just this. As always, if we write it down correctly, we don't make any mistakes, and then we can simplify. 1 over 2 theta. The 2's not doing anything for us. That's just the height of this line so that everything integrates to 1. And then I've got this indicator function, and I'll just write it into the numerator, that the xi's themselves are between negative theta and theta. And so we write that just a little bit differently. Proportional to 1 over theta raised to the n. That's just that part. I got rid of the 2, so I'm just going to write down proportionality again. And then we wrote it down this way, that we had only 2 indicator functions that really matter. This is going to be x1, minimal order statistic is bigger than theta, negative theta, and xn, the maximum, is less than or equal to theta. I guess I wrote round brace here, an equal sign there, so I have a little bit of a typo on here, but saying that, nothing would happen if I ended up making that error, because the measure at that endpoint is 0. But I guess we should probably do that. That's simply because I didn't include those points in the notation. Okay, so we've got this. We kind of talked about last time, this is showing us decay, and this is showing us the boundary of everything. And I drew this picture, and somebody asked me about this last time. Which data point did I draw this with respect to? So here's my likelihood function. So this thing right here is just 1 over theta n. So it's basically saying as I make theta too big, probably not likely, but what was this point right here? It has to do with this, those 2 conditions. So I actually know what point this is. I know what it's stacked up on. And that's why I kind of insist that minimal sufficient statistic is really defined by whichever one of these is closest to the boundary. And we know, we can tell. So if I ended up getting rid of this sign right here, and I just looked at the magnitude, I really just look at which one of these is farther out in the space, which one's magnitude is bigger, that's the minimal sufficient statistic. That's the one that's actually closer. So you can tell just by looking at its magnitude. And so this is going to be the maximum of x1, and I'll say absolute value, in xn. And I'll say absolute value there too. So I'm perfectly careful in all of this. So whichever one of those is bigger. You'll notice that if xn happened to be on the left-hand side of 0, that its magnitude wouldn't be very large. And it's the one that's walking farther out here that's telling us about theta. And that's consumed in this. And so that covers all my bases. So it turns out this thing is really one-dimensional. So I had a couple questions about that in the last couple hours. So that's telling us that it's one of these things is the maximum likelihood estimator. So the maximum likelihood estimator is the answer to this. How can we tell? It's the likelihood that's going all the way up, right there. This is a very good example. in terms of addressing that question that popped up in the last lecture that we were a little bit confused about at first, we'll need to read real carefully those things. And so, this is a very good example where Kramer-Rao does not apply. So Kramer-Rao doesn't apply in this example, and all of that stuff that we said about maximum likelihood finding is still true. It's just that the maximum is on the boundary. And that's what I alluded to last time when I said, well, sometimes when your maximum is on the boundary or something like that, you'll see some conflict, you know, where Kramer-Rao doesn't even apply. It's not even a real thing. We'll get into that soon. I want to do something more fun in the meantime and touch on this mixture identification. That's what I've been building into my classes for the last couple of years, something a little bit more modern, something that we can do readily. 20 years ago, this was a research project. So people were writing research papers about solving this problem over here. Nowadays, it's a homework problem. So, super useful. If you can do this, you can kind of almost do anything. Now, the EM solution to this problem isn't the only solution going. So this is a maximization technique, so it's akin to maximum likelihood. There is an averaging process in there. And that's kind of like Bayes. So this is a hybrid technique right here. And you can say what you want, that it's Bayes or not Bayes or whatever, but I assure you Bayes' rule pops up in this whole thing. And so it's kind of half Bayes, and we'll look at that, and we'll look at the maximum likelihood part of it too. There's a Bayesian solution where you run a Gibbs sampler, MCMC algorithm over this, and I'm going to reserve that for my Bayesian class. So if you're so inclined, sign up for 5444, and I'll show you the whole Bayesian analog to this. I'll show you the maximization technique. At least Sierra will show it to you, and I'll say a few things about it. So that example, I think we've covered enough of it. Let's talk about mixtures. And by the end, I'll tell you what EM is. And Sierra will recap all of this, tell you what EM is, and then show you how to run everything. I'll show a very simplified example to show you that everything that we're going to get into is ultimately pretty easy to code up. So what you end up coding up is simple. We're going to go through the theory, proofs that this thing works, so on and so forth. So lots of stuff. At the end of the day, the EM algorithm induces a little iterative procedure. And there is a little bit of math involved in being able to code up the right thing, but once you have it figured out, it's pretty easy. Okay, just redraw this picture. So I'm drawing a 3-component mixture model. Might have one distribution, I'll call this F1, and it's got some parameters in there. I'll just denote all this as X given theta 1. I've got some other distribution. You would probably be inclined to call me out if I said those are both distributions, because there's no way both of those integrate to 1. So let me make this one taller and skinnier. Try to at least make things look like distributions, maybe. And then maybe there's another thing out here. Okay, so I'll call this F2. X given theta 2. And this is F3. And actually, let me just do this like this. Let's make this one look skewed. F3x given theta 3. And so in my notation, the parameters I'm writing down just have this fairly arbitrary meaning. So it's whatever parameters underlie these distributions. So you might look at those and say, well, those look like Gaussians, so my theta is probably mean invariance, but I just drew something that looked heavy-tailed over to the right, so you're not sure what this distribution is. These distributions, the parametric forms, don't need to be the same. They can all be different, is my real point. And they've got some parameters that underlie them. So maybe this is a weird, skewed sort of Cauchy thing, is what I'm thinking about. So, but it's just an example. Okay. here's what we do. If we wanted to sample from this distribution, and we've done this before, so in the beginning of class in Sierra, maybe we should just run a simulation real quick. So I've got some piece of code that I just sent you called mixture simulation. Let's run that. See if this works.
Why can't I share my screen? Host disabled the attendee.
Okay, let's not worry about sharing a screen. Why don't we just project
Okay.
it? And then they'll be able to see it.
Yeah, that's true.
This is really just a replicate of the old Bootstrap code that we used, and the model that we were sampling from back then was a mixture model. It had some weights on each of the components, and then basically I was drawing from some normals and shifting them around. You want to hit run and show them what that looks like if they run this code? This is the same mixture model that's inputted into your Bootstrap code. There we go. So I think that's good for now, just as a reminder of what a mixture is. This is a normal mixture model that we just looked at. I'm going to tell you what we just did on board. So let's get rid of that. So this is what the code does that Sierra just ran. And again, this code is in the Bootstrap code that's online. So first I drew some arbitrary distribution. I wanted to make my distribution look weird so that you could understand the central limit theorem and all those important messages that we saw before. What I did is I simulated from a mixture. And so this mixture model right here, the distribution, could be written like this. I'll just write it out real simply at first. Pi 1, fx given theta 1. I'll be specific about that. That's f1 plus pi 2 fx given theta 2 plus pi 3 fx given theta 3. I'll put some indexes on this distribution as well. There are some conditions on all of this. All the pi's are greater than 1. Or greater than 0, sorry about that, and less than 1. So all of these things, each one of them is a number between 0 and 1. And they sum to 1. There's 3 of them here. Pi I sum to 1. So there are probability weights of coming from these various distributions. I've said that these are distributions, so if I integrate under their densities, each one of these will integrate to 1. And so if I add all of that up, I integrate over all the x's, these will all turn into 1s, and if I sum up all of my pi's, everything will sum to 1. And so this distribution right here, which is represented like that, sums to 1. I could write this down fairly arbitrarily, and I could end up giving this function a name. And I could say this is f of x, and I might write down whatever this function is. I won't index it any more than it needs to. And I write down theta 1, theta 2, theta 3, and there's also these pi's in here. Just has all of these unknown parameters that it's conditioned on. Let me back that up. One more time. Given all of these various parameters, so I've got theta 1, theta 2, theta 3, and I've got my pi's. So all kinds of parameters underlie this thing. So I can give it some general notation. I'll write down, this is F mixture, M for mixture. Give it a name. So mixture models can be decomposed into relatively simple models. Okay. So what we did when we sampled from everything is we had 2 steps that we walked through. These are the same 2 steps that we saw at the beginning of class. So to sample, just a heads up, I'm going to be giving you a homework assignment where you sample from a mixture model that you create, and then you infer all the parameters behind it using the EM algorithm. So I'm going to have you do all of this, but not only in one dimension, you'll do this in higher dimension as well. So to sample, do 2 things. First, I'm going to sample which component I came from. So I'm going to sample one of these 3 distributions. And I'd like to give that some notation, and I don't have that notation really built in right here, except for this particular index. And so I might be a little bit more explicit about that. And so let me give myself a little bit more notation. I'm going to write down C, which is going to be, in our example, an element of either 1, 2, or 3. So this is going to be the component number. Oops. Swap a blue pen for a blue pen. I'm going to call this the component. Some people call these labels. So, but basically they're the labels in the problem. I'm using a language that's very akin to clustering when I say this. It's labels. For those of you that are into clustering, this is effectively a one-dimensional clustering problem. You can turn this into a higher dimensional model-based clustering algorithm. So mixture model identification is clustering. Just write that down. And so sometimes I'll jump back and forth, and I'll either think of things as the component numbers or maybe the labels if I'm talking to people that are inclined to study clustering. But basically, we need to figure out which cluster they live in. So I might say or clusters. Cluster number. Okay, there's 3 of them right here. So my new notation for my distribution, I'm just going to write down like this. FC X given theta, whatever those parameters are, indexed by C. So that's exactly the same thing we had before, but I'm going to add just a little bit more superfluous notation. This is seemingly superfluous. I'm going to write down C right there as well. We're going to come back around to this, but I'm just going to treat this eventually as a random variable. We're going to have to do some inference on that. And so I'll just say what we end up getting is things that are distributed according to these various distributions. So this later on we'll treat. It seems a little bit redundant to put that in, but I'll just say this is what I wrote down before is FCX given theta C. So just like we had over here. So what I'm going to do is I'm going to first sample C. CI, if you will. So this is going to be for every iteration that we have, every data point that we sample, under this curve. So each one of these data points, xi, came from a particular component. And I'm going to be really specific about that. So ci is going to come from a multinomial distribution. And this is going to have 3 parameters in here. Pi 1, pi 2, and pi 3. Those probabilities are these probabilities. So what we're going to do first is flip a coin and decide which component we come from. And then, once we know which component we come from, we're going to sample from that particular distribution. So xi is going to come from f x given theta ci. Where this thing is getting plugged in right here. Let me highlight this in red. So the notation that I've just used tells us that we just jointly sampled ci and xi. So we sampled both of them. So we have a joint realization. But all we're going to show you is the xi's. So I'll just make a note. But you only get to see the xi's. I goes from 1 to n. So we're going to repeat this process n times. We're going to get all of these data points. And these data points are going to have histogram representations that look roughly like the underlying distribution. As n gets bigger and bigger, this histogram will look like that density function. So 2 steps to sample, and that's what our code does. It flips a coin, 3-sided coin in our case, and then samples from the relative component. So a pretty straightforward thing, and that is a distribution. So just key point. Xi and Ci were both random. Hence, I like this notation right here because I'm treating it as a random variable in the process, so I should denote it as one. We're going to take advantage of that later. So I think with the right notation, this problem is actually pretty simple. Ultimately, we need to infer this as well as all the other parameters in the model. Those. Okay. So let me give you a concrete example. Let's say xi is going to come from this distribution. So I'll say C goes from 1 to 3. And if you'd like, I could put the C in there as well. I'm going to say that this thing right here is normally distributed. So I'll say that that's normal with theta C being mu C and sigma squared C. Those are the 2 parameters that underlie a normal distribution. So that's what we need to infer. And so 3-component mixture model. Actually, let's make this easier. Let's say 2-component. So I'm going to sample I goes from 1 to n. So my example looks like this. mu1, mu2. And this is sigma 1, sigma 2, sorry. And sigma 1 is over there. And so we need, I'll say given, and how about this? I'm going to make this problem just a little bit simpler than what Sierra is going to do. I'm going to say these are known. So Sierra will show you what to do when they're not known. So really, we're just simplifying some of the notation in the example and the steps. So our goal is going to be given x1 to xn infer mu1, mu2, and pi1 and pi2. Now, there's kind of a couple cases that you have to confront. The real case is that you don't get to see any of the c's in any of this. You only get to see the x's. But I want to entertain the case first of what do you do when you get the c's. So let's just look at that. It's pretty easy. So this is the unrealistic case. It does pop up every once in a while. Every once in a while, sometimes people know the C's. Say 99% of the time, I'm confronted with cases where I got to figure it out. Okay, so simple case. Just draw my picture. Make this easy, you get to know these. You don't get to know those, and you don't get to know their weights. Their weights are going to be determining how much area is under these two curves. So if pi1 is very big, this will have a lot of area. If pi2 is very big, this will have more areas. This does have more area. And I want you to conceptualize that the total integrated area under these two curves is 1. So it's a distribution. Simple case. You get to know CIs. So you get to know all of these. C1 to Cn. So these are paired with the observations along this axis. So the x's live here. And there's very little question, even if I didn't tell you the C's, if I did tell you what the mu's look like, what the distribution looks like, you could probably tell me that data point right there came from component 2. These ones in the middle are a little bit murkier, and we'll touch that in a moment. But say you get to know the C's. What you actually know about the X's is which component everything came from. And so to do inference, let I'm going to write it down like this. X1 be equal to the collection of data of x's. So this is everything that has CI equal to 1. Okay, so they're all data points from component 1. So that's going to be all of these data points. Let me just point to those. I'm going to say they're those right here. That's X1. Okay, this collection of data. That's loaded there. Sierra is going to have some notation for you, and I don't want to walk all over her notation right now. That's why I'm being a little bit more general about this. X2 is equal to the collection of data points from component 2. So basically, I just looked at where CIs were equal to 2, and I took those corresponding X's. So let's say I give those to you. Those are here. So that's X2 stuff. Okay, so you have 2 vectors of data. And they can be from different lengths. If pi1 and pi2 are very different from each other, you'll end up having different data sets, different size data sets. So the question is how do you do inference? And the answer is easy. You do all the stuff we already know how to do. Flexible, right? Okay, so how do you do inference? You don't need an algorithm. On pi1, pi2, mu1, mu2. And we said we know the sigmas, just to make everything easier. So this is pretty straightforward. So pi 1 hat. I'm just going to propose something real quick. I'm going to look at the frequency of times I sampled from component 1. And you can probably convince yourself pretty quickly there are a lot of different estimators that will induce that. And so I'll let you defend this, but this might be an MLE. This is equal to the size. I'll write it down this way. So number of data points in X1. So it's just a count of those things divided by n. So this will be my size of X2 divided by n. So I might ask you, why is that the MLE? Since my class can't respond to me, I'll just say, isn't this a lot like the Bernoulli problem? I've got 2 things. How do I estimate P? These are really interacting as like P. And so this is the typical sort of Bernoulli estimator for a probability. So that's the MLE. Might be a MOM, might be a Bayes estimator, might be all kinds of different estimators. So a lot of commonality on estimating these things right here. So And probably won't surprise you to find out, since I know the component labels, mu1 hat is equal to the sum of the xi's such that these xi's come from cap x1. And I'm going to end up doing this to the size of x1. So same notation. I divide by n. Similarly, mu2 is just the average of the points from component 2. Fun with notation.
Are you sure it's in?
Ah, thank you. Sierra's on top of things. She just told me fix that up and divide by size of x1. So that's what n is up there. So this will be divided by the size of x2. Same notation. So this is just x2 bar. This is x1 bar. So it's just the averages of these two sets right here. No surprise, that's the MLE. Super easy. There's some Bayesian ways to think about this as well, and there's method of moments ways of thinking about this. And this would be an entirely uncontroversial solution. If you didn't know anything about the problem, most people would probably come up with this. No algorithm required. Because I know the C's, real problem is you don't know them. That problem's much harder. And so I want to just point out that the C's are missing. So note, CI's in our realistic case are missing. So EM is a missing variable algorithm. There's always something missing, and that's where the expectation step is applied. So we try to average over things. And so we're going to treat C as a random variable, and we're going to try to marginalize it out of everything. But they're ultimately missing. We don't get to see them. There's also some other language for this. Some people might say this is latent. So don't get fouled up by this word. It just means you don't get to see it. Unobserved, so on and so forth. Okay, so if I got to know the mu's, if I happen to know these, and I happen to know those, this problem isn't too hard. So if I did know these things, hypothetically, and I gave you this data point right here, you'd probably say, well, it's to the right of the mean of the second distribution, so that came from component 2, I'm pretty sure. And I would probably agree with you. And any algorithm we built will probably agree with that as well. Even if I pick this data point right here, it's probably coming from component 2 because the tails don't overlap over there. And probably any algorithm is going to say that came from component 2 so long as you know these two things. So we get a little bit murky around here, but as we budge past that overlap, then we become pretty comfortable saying all these data points came from component 1. So that is because you know knowledge about the parameters. Unfortunately, you don't know anything in this problem. You don't know the parameters, and you don't know what the labels are and everything. So these two steps of this algorithm we're going to talk about are going to be iterating between inferring those two things. And if you have experience with fixed point type algorithms where you iterate back and forth and then it converges in on some sort of a solution, then you're probably comfortable with that idea that this will converge to something if I try to figure out what C's are and then I try to figure out what the parameters are and then I move back and forth. That's what this algorithm is going to do. I want to show you what EM is, and then I'm going to kind of call it a day. So I want to tell you what the 2 steps are, and then I'm going to write down how that gets implemented on this very simple problem. I know what it is, I know what the answer is. It won't be entirely obvious to you that this is the correct algorithm, but Sierra will convince you next time these are the right steps. So let me just show you what EM is. So I'm going to generalize some notation real quick. So I'm going to say let your likelihood function, so this is likelihood, be conditioned on all of my data. No surprise, that's what likelihoods are. That's one of the things I really like about likelihood functions, is it conditions on the data, and minimal, or at least the sufficiency principle is built into this. So I don't even have to concern myself with it. And I'm going to expand my notation a little bit. A lot of times I just write down theta over here. So these are going to be parameters that you want to learn about. And I'll say these are parameters you want to maximize. So an example of those. Back to this problem right here. The example is going to be mu1, mu2, pi1, and pi2. If we didn't know the sigmas, you'd need to include those as well. But there's also some other variables. I like to think about them as parameters. I like to think about them as random parameters because I'm a Bayesian. All my unknown stuff, I hit with a prior and I upgrade. Not everybody will explain it this way, but EM does exactly that. They apply Bayes' theorem. There are other ways of explaining it, but I don't think you get to say that you're doing probability theory unless you're invoking Bayes' theorem. Some other people have different names for this operation, but anyway you skin this cat, Bayes' theorem. So there's other parameters, and I'm going to say these are missing parameters. So these are latent or missing. You don't get to see them. Now, in the very typical setup of EM, the EM algorithm, these can be anything that you just don't get to see. So if you're a social scientist and you gave out a lot of surveys, they might be your blank entries. And you will need to model their dependence through some sort of model. Why are they missing? What was the mechanism for missing this? So if you take a missing data class ever in your life, they'll teach you about 3 different forms of missingness. So missing completely at random, things that are missing because they depend on the responses of the sampling distribution, so they depend on the actual random variable themselves, or are they missing because they depend on other stuff that you get to see. And so different mechanisms of missing. This isn't a missing data class, but I will tell you in the context of our example, there are seeds. So for this clustering problem, mixture identification problem, the missing stuff is the seeds. But we're going to at least teach you the proof generally and show you that this algorithm can be applied to any problem where there's something that's latent, something you want to maximize, and you can write down the likelihood function. EM is applicable to that problem. So, example. C1 to Cn. So lots of notation in this problem. And this is one of the things that's going to mess you up if you don't study our notation. So lots of things going on, lots of indices. Okay, here's what EM does. It does 2 steps. Algorithm. It's 2 steps. And these steps iterate. So you do these steps over and over and over again. So I'm going to put this into a for loop. And with any iterative algorithm, we need to initialize. So we need to start this whole thing. So I'm just going to write down that our step 0 is to initialize. And so I'll just pick theta to be something. So we're going to make a guess at what theta is, and then we're going to run our algorithm. And it'll hone in on what true theta is. And if you initialize very far from the truth, very far from what these things are, then it'll take your algorithm more steps before it gets there. How do you assess convergence? You run it for a long time, and you see that your answers concentrate somewhere. And then you run it again, starting it from somewhere else, and you see if they concentrate in the same place. And you do that a whole bunch of times, and then you become convinced that maybe you found the stuff you're looking for, i.e. the maximum of these parameters. So let me just write down the goal, just so we're real clear. Goal. It's going to be to find theta hat, which is the max of theta. And in our problem, that's all of these. So we want to maximize over the parameters we want to talk about. In our case, these things. Okay. Like this algorithm because the 2 steps are finding the expected value of something and then finding the maximization of something. This is the most confusing part of it, step 1. Step 2 is pretty easy stuff. So I'm going to introduce a function. It's going to depend on my last step. And this is going to be finding an expectation. So it's going to be the log likelihood function. Our missing stuff right here. And I'm going to fill out the second step, and you're going to be looking at this expectation and saying, looks easy enough. But if you haven't noticed, I haven't said what expectation that is. So we'll come back there in a moment. But here's how the algorithm continues. It updates theta t by finding the maximum, I'll say arg maximum, over theta of q theta given theta t minus 1. And that's updating our new value right here. So I compute a function, and then I maximize that function. And then I compute the function, and I maximize it. I iterate between these two things. This algorithm will work even if you don't do a full maximization right here. It just needs to increase. So if you keep increasing this value in terms of this function that we keep getting, just pick a different value, something that increases that. As I move away from this thing, it will eventually work. So you don't need a full-blown maximization right here. You just have to climb the hill. So just like all maximization algorithms. If you're making your progress, you don't have to go to the hill, up to the top of the hill fast. You just have to be making progress. So I'll just make a note about that. Note. Theta t just needs to increase q. Okay, so I used to go climb a lot of mountains on bicycles and on my feet, and I would get the same question all the time. How do you do that? You know? How do you just, and it's real easy. So one foot in front of the other, and I just make a little bit of progress, a little bit at a time. So how do you climb a lot of mountains? You keep going up. That's it. And so you don't have to be fast at doing anything. So there's one time out at Yosemite National Park, and somebody wanted to climb up Half Dome, at least the back side of it, take a hike, go take a climb up it, and wanted to do this thing. And my friend got rather tired on the whole thing, and I told him that I could prove to him that if he just kept putting his feet right in front of each other and we just go up the hill real slowly, we're going to get to the top. So there's a mathematical proof out there somewhere. So I'll let you work on it. Let's go back to step one. I have to be explicit about what this expectation is over. And so I'm going to have to write that down. You'll notice in my notation, that thing over on the right-hand side hasn't appeared. And somehow I got rid of psi right here. So what we're doing here is we're averaging over psi, conditional on theta t minus 1. And so we're taking this expectation with respect to this distribution. And so we need to figure out in this algorithm, what is this distribution? So let me just write down more clearly what step one is. Step two is I get some function and I maximize it. I think we can all understand that. So step one looks like this: expectation log likelihood function. Some people call this the complete likelihood. I just call it the likelihood. And this is with respect to this random variable. And in our problem, C's were random in the first place. We actually know how they were generated. We know what was going on there. We know the model dependence. Sierra will walk you through all of this next time. But this thing is just an integration. So I'll just write down, in our case, it's a sum, but it's just going to be the integration in general for log likelihood function times this distribution. I want to talk about this just for a moment. So in general, this is like a high-dimensional integral. Okay? Now keep in mind, our psi function, our missing stuff, are these C's, these labels. And so we're just summing. I always write the integral sign down, and I never tell you what kind of integral I'm doing. But we're just summing over the possible C's in everything right here. Question is what is this distribution? And that's what we're going to figure out. But I want you to think about it in the context of the mixture problem that we're solving. Just remember this. This sort of thing. And I hopefully convinced you that if you knew what these distributions were, you knew this thing, you knew the relative area of this to that, that's telling you what the pi's are, that if I gave you a data point, oh, and I do want to be more careful right here. I want to tell you that everything is conditional on X in all of this. You always have the data in hand. You always know what the X's are in everything. So everything is conditional on X. A lot of books won't write that down in the notation, but X's are there. You get to know the data. So let's just think about this. In the context of our problem, so this is our example, our two-component mixture. Psi is this C thing, okay? So this is at least going to be one of them. So part of psi is each Ci, okay? Let's do C1 to Cn. So let's just say, if we're trying to figure out want to learn Ci, some particular one, and you know Xi. So we do know Xi in all of this. So this notation is, I get to know all of the X's, but I'm just going to focus on one particular one. It turns out, this is the only one that can tell me about Ci, because it's the one that was generated with it, if I already know these. And this distribution is conditioned on what I think the parameters are. They're not fully right yet. But as this algorithm progresses, those are going to get better and better and better. So all of them. So best guess at the last step. Let's say you did know everything and those were pretty good answers. If this algorithm is converging, then these answers are getting better all the time. Let's say they were actually close to these. Or at least I had the pi's and I had the mu's real close. And I saw this right here. This is Xi. And I want to put a probability distribution on Ci being 2. Component 2. How do I construct that probability distribution? So the question is, in the context of star, is how do we find probability distribution for Ci given all of your old parameters? So theta t minus 1, what is that? That's mu t minus 1, 1 and 2. And pi 1, t minus 1, and pi 2, t minus 1. So that's what this is right here. And if I knew all those, none of the x's can help me. That's the conditional independence property. If I knew the parameters, none of the other data helps me. So if I think I know the parameters and I'm conditioning on them, then I only need that one data point to try to infer the CIs. All the other stuff is helping us co-estimate the parameters. That's what happens in the next step, right down here. So how do we get that? I'm going to leave this as a big question mark. And I'm going to remind you you know fx given theta and c. You know how you sampled x given c. This is asking you to flip that thing around and figure out, given x, what do you think c is? And if you think of this as a probability and you treat it as one, you just were a Bayesian. And so you have to come up with what your prior is on everything. Sierra's going to walk you through these steps next time. But this is going to average over the log likelihood, which, because of the monotonicity of log, if I maximize over log likelihood, it's the same as maximizing over likelihood. I'm going to convince you, or Sierra will next time, that maximizing the expected log likelihood is like maximizing the likelihood, except we're averaging out this stuff right here. So we just average this thing away. That's like what a Bayesian does. And then I maximize that. So let's just look at the code real quick. I've got just a quick version of this, and then we'll be done. That code is called EM example. Say a few things about this, and Sierra will pick up. She'll go through the proof that this algorithm actually works. Seems conceptual that it might. It will be more specific. And I've got some example. And right here I've just noted what my mixture model is. So my mixture model is going to be P, some number between 0 and 1, times a normal, where I've got mu1 and a known variance. My second component is going to have the same variance. It doesn't matter. I just did it for convenience. I'm not going to infer that in this piece of code. And it's got some mu2 that I want to infer. You'll notice that if I've inferred P, I've inferred 1 minus P. And so this problem has maybe one less degree of freedom than it looks like without talking about what the actual mixture weights are, their probabilities. They sum to 1. Okay, so I'm going to simulate some data under a truth. And the name of the game is going to be to run this algorithm and try to learn what these are. And this algorithm encodes these two steps. What I want you to do is just run the algorithm right now. See how it works. Okay, so this is the data that was simulated.
Is there another plot?
You just run it again, and then let them see what goes by. Okay, what you see down here, lift that up. Lift up that window so that we can see the muse. There we go. What we can see that goes by is updates of mu and p. Let's look at the code just one more time. So the code.
Which one do you want to look at? The mixture sample?
That's what we're talking about. Let's go down. No. Yeah. So we've got these parameters that we want to infer: P, mu1, mu2, and it's 2 and 10.5. And P true is P true, the probability of the mixture weight is 0.7. So the answers are 2, 10.5, and 0.7. Now I want you to run the code one more time with that stuff flashing. Okay, let's initialize it somewhere different.
Where's your that's your true?
Yeah.
Where's your initialization? It's a hard part we have to go through here.
There we go. Okay, so what I want you to look at right here is the way that I've initialized this problem is every time I run it, it's going to pick a random initializer. And so it picks mu1 and mu2 to be one of the data points at random. So I just pick one of the indices and I plug it in, and I grab one of the data points right here that I've simulated. And this is going to be a uniform random right there. So let's run the code just one more time and show them that this is changing every single time. What you'll notice this is just the sample data that's going to change every single time we run it.
Here,
yeah, we don't need to see it, I don't think. That's what the distribution looks like, and our answer is that. Run this one more time. I want you to see this is 10 and 2, 0.3, and 0.7. I want you to see this. These things just flipped. They're not exactly the same. So the algorithm's getting close, and it kicks out after some amount of time. This data that we just generated is slightly different, so we expect these numbers to be different. But what we just saw is them flip. And that's because when we end up calling something component 1 or component 2, our computer doesn't know which bin we're holding that in. And so that's arbitrary. And this is what's called label switching. And you flip them around. And it's something you need to be aware of when you're reporting the answers, what you're calling component 1 and component 2. Run it one more time. And it's flipped again. So they tend to flip. And you have to be aware of all of that. Let me show you without showing you my code. So you're just going to run you through this. You're going to be coding it up yourself. And that's why we haven't shown you all the guts. But I want to show you just real quickly what this code is doing. It's really just repeating this step. Compute. I'll write it out like this. Q, mu1, mu2, pi1, pi2, given where I think I was last time. Mu1, mu2, t minus 1, t minus 1, pi1, and pi2, t minus 1, t minus 1. It turns out we can compute this function in closed form for this problem. So remember what this was. This is the expected log likelihood function. And it turns out we have a closed form solution to that, for this problem. And Sierra will show you that. And that closed form solution has a closed form solution to maximizing everything. And so what this really is going to be step 2 is you're just going to be maximizing this. So this is max q theta given theta t minus 1. And it turns out there's a closed form solution to this as well. We know what it is. And so it turns out mu1 hat is going to be a weighted average that we compute at every step. 1 to n. This is going to be a weight. Let me just divide by the sum of my weights. And pi 1 is just going to be your typical frequencies. So I'll just write you as an example. My code's actually really simple. This is going to be 1 minus wi over sum of 1 minus wi. So these w's are weights. If you think xi is an element of component 1 or component 2, and if you're like me and you hear the word weight, you think the word probability. So this is a probability, and we know there's probability. So what is this thing? This weight is going to be the probability that Ci, I'll say, given theta t minus 1, given xi. So these are all our old parameters. But this is that probability function. And I'll write this down as C is equal to 1 right here. I'll be just real clear about this. So that's my probability for this. These are the flips of this, but this is going to be the probability that Ci is equal to 2, given xi, and all the parameters. So it's this probability calculation, which is Bayes' theorem. And so that's how we estimate the mu's. If we knew with certainty that the x's came from particular component numbers, then these w's would be either 1s or 0s, and they're not in this case. So this just ends up becoming a weighted average of everything. So that's what the math ends up doing. The pi's are pretty easy to get as well. So the pi's in all of this I'll write down pi 1, update, oh, and these are just my updated values. This is going to be the sum. I goes from 1 n, right here, of these probabilities. I'll write it down like this, wi divided by n. So this is going to be for c is equal to 1. So it's that probability, where that's a 1. So it's just this average. And accordingly, when this is component number 2, so maybe I'll just write this down as a k right here, that this is the general equation. So here's the point. All I'm doing is I'm running in a for loop real quickly these averages. And k is going to go so 1 or 2. And all we're really doing is updating these at every step. How do we update these? Well, given our answer at the last step, we plug those in, we get new probabilities that we update. Given those new probabilities, we compute 4 new averages. You don't actually have to do the second average right here because I know whatever this is when k is equal to 1, I know what both of them sum up to. So you don't have to compute the second one. You have to compute both of these though. And so the algorithm works like this. I've got this enclosed form. I get rid of that. I've got these explicit maximizations that we do. Sierra's going to show you how to do that using Lagrange multipliers, possibly. I don't know if she's going to work these out entirely for you because I think we're going to ask you to do some of that on the homework, is to show you that these are the answers. So I think what we'll do, instead of deriving everything explicitly, is ask you to do some of this on the homework, and Sierra will try to explain the steps. So, to conclude, this is simple. Every step I compute these probabilities, then I compute these things. Compute the probabilities, compute those sums. And it turns out that's what the EM algorithm is asking me to do. And this thing will converge to the maximum of all of these things that you want to learn about. So I think that's it for now. Thanks you guys. Sorry for going long. See you next time.